Hello, everybody. My name is Shachar Chaikin, and today I'll present you one of our recent publications titled Long-Term Warming Reduces Fish Biomass, but Heat Waves Shifted. This work is about disentangling the impacts of chronic and acute warming on fish biomass, and was done together with Juan David González Trujillo and Miguel Bastos Araujo. This talk was also given in the IBS conference that was done in Aarhus 2026. I'd like to start by saying that long-term warming is bad news for marine animal biomass. We know that from global simulations that should suggest that biomass is projected to decline by about 17% by the next several decades. Biomass drops by about 5% for every 1 degree Celsius of warming, based on the fish meep compilation of ecological models. So what we are still lacking is the impacts of marine heat waves on fish biomass. We know that long-term warming is a big problem, but the acute events future is uncertain. We know about one big study that compiled a lot of bottom troll surveys and found that on average, the biomass log ratio of marine fish does not change with respect to marine heat wave cumulative intensity. So there's no impact overall. However, different studies coming up with different data sets and different taxa showing that actually it could be a thermal position dependent effect. For instance, populations in the cold edge might respond positively or won't respond to marine heat waves, while warm edge populations are those that are more susceptible to their impacts. So there's a big question mark here about what are the impacts of marine heat waves on marine species, and maybe they are more local than we think. So our oceans are facing a dual thermal threat. On the one hand, we have this warming signal, long-term warming, which is quite steady over the years, but we have those spikes, are actually more correct to say those marine heat waves that are acute events that could have different impacts through different processes. So there is this dual thermal threat as composed of the long-term warming and the short-term warming. So we know that they are acting simultaneously, right? We have the constant long-term warming, but at the same time, sometimes we have those marine heat waves. We're not sure if their impact on marine species are the same. More specifically, we try to understand if their impacts converge or diverge. So it could be that long and short-term warming have similar impacts, but it could be that they have different impacts. We're not sure about that. This is one of the goals of this study. The second is about the magnitude. Are the effects of equal strength? Could it be like 10 years of long-term warming are equivalent to one big marine heat wave? These are questions that we're not sure how to answer, but we try to give some evidence about that. And finally, perhaps there is an environmental context. It could be that populations in the cold edge are more resilient to marine heat waves, but we're not sure how their response will be for long-term warming, and the same for warm edge populations. So these are questions that we would like to answer. So in order to quantify the climatic impacts on fish biomass, we first of all had to gather the data. We used scientific bottom troll surveys. We compiled big surveys. The first compilation actually is a fish globe. And we added to it the Mediterranean bottom troll fish surveys, also known as the MEDITS, which is now available through the European Commission. We took these data sets, we wrangled them, we cleaned them, we categorized them into hexagons, which are standardized units, and we binded also seabed temperature data from the Copernicus marine surveys. So we have these daily temperature data. The second step was to estimate the biomass change. We used there the log biomass ratios, which informs us about the magnitude of change in biomass year over year. And we use different predictors to account for thermal stressors such as the decadal temperature rates or decadal trends that represent the long-term warming, but also the cumulative intensity of marine heat waves, and we compared relatively warmer to colder years. And of course, we bind it inside the thermal position of the populations in case the effects are very localized with different responses for cold versus warm edge populations. We also use the data from GBIF to gather to create this thermal position. So we had to have occurrences for every species. So this was another data set that we use. And finally, once we have everything together, we used generalized linear mixed effect models to estimate the effects of the long and the short-term warming on fish biomass. Overall, we have data spanning the Mediterranean Sea, the Bay of Biscay, the North Sea, Baltic Sea. You can see also some points in the Barents Sea, and in the west part of the Atlantic Ocean, such as parts of the Bay of Fundy, Canadian shore, the US shore, Gulf of Mexico, and parts of the Northeast Pacific Ocean. Overall, we compiled 30 years of data, which corresponding to almost 34,000 populations, more than 1,500 fish species, and eventually the sample size in our models, more than 700,000 annual biomass change estimates. So year over year, how the biomass of those fishes are changes within each population. So I'd like to start with the results. What you can see here in the y-axis is the change in biomass in percentages. And in the x-axis, we have the temperature difference, which are warmer on the right side of the x-axis and cooler years on the left side of the x-axis. And what we found as a main effect was a positive response, meaning that on average, warmer years result with increased biomass, which might be a bit counterintuitive, right? But once we accounted for the thermal position, which is the interaction of the thermal position with the temperature difference, we found a significant interaction, which informs us that there is a biomass booms at the cold edge up to 176% and declines at the warm edge, about 42% decline. So the effects are really localized. It depends on the context and the environmental context of the species, of the populations. So warmer and colder years create distinct winners and losers. You can also see that there is asymmetric response to warming and cooling. So for instance, if you observe a year that is warmer in 2 degrees Celsius and one that is cooler in 2 degrees Celsius, you can see that cold edge populations during warmer years benefiting much more than warm edge populations in cooler years. So there's short-term warming. Eventually, we can summarize that catalyzed cold edge dominance because in warmer years, we get much more increased biomass in the cold edge. What about the effects of marine heat waves? We tried to compare results with the studies that I presented in the first few slides. In this case, in the x-axis, you can see the annual cumulative intensity of marine heat waves. And the main effects we found was actually zeroed. So marine heat waves show no overall effect on the change in biomass for marine fish in the data that we cover. This is a quite similar result to what Fredstone et al. Showed in the Nature paper, but the nuance that we can give here is that actually location matters a lot. So if you account for the interaction with the thermal position, we actually see that cold edge populations gain a lot during marine heat waves and warm edges are declining. So we cannot say that there is no effect of marine heat waves on fish biomass. The effect can be zeroed if we do not account for the thermal position of the populations. And this more relates with other studies showing that there is an environmental dependent effect of marine heat waves on marine taxa. So heat waves are bad news for warm edge populations. What about the long-term effect? In this case, we examined decadal seabed temperature trends. This is what you can see on the x-axis. So positive values are for decadal warming rates and negative values for cooling. We do have some, not a lot, but some evidence for that too. The y-axis is just the same. And what we found here is a negative main effect. So Long-term warming equals to widespread declines. For every 0.1 degrees Celsius of decadal warming, fish biomass declines on average by 7.2%, which sounds quite disturbing. In this case, the interaction with the thermal position was insignificant, meaning that it does not matter if we're talking about a warm or cold edge populations, both are impacted negatively by decadal warming trends. So thermal position does not moderate biomass declines. We have here eventually diverging impacts of warming on fish biomass. Thermal position dependent effect for the short-term warming, such as marine heat waves or warmer and cooler years, but homogeneous long-term loss. And I'd like to give here an example of the European sprat, Spratus spratus. On this map, you can see the populations that are covered within this study. We have populations that can be considered in the warm edge in the Mediterranean Sea and parts of the Bay of Biscay. But then we have those cold edge populations in the North Sea, the Baltic Sea, and the Barents Sea. And we draw here the biomass response, and you can see across thermal position, you can see that there is a negative trend, meaning that for these species, we can see that there are warm edge declines, cold edge gains in warmer years. And the effect that you can see here is true for more than half of the species that we examined, which is quite a lot, more than 700 species that show these kind of patterns. So it raises a big question. Can these local gains be exploited in the cold edge? Because we know that if there are marine heat waves, then the cold edge should benefit. Can we exploit those gains, or can't we? Or shouldn't we? I think this study screams for a bitemporal management plan. What I mean here is that we should have a long-term strategy where the focus is about mitigating the biomass decline in the face of long-term warming. So in this case, we should prioritize conservation across all populations because on average, they are all losing in the face of the long-term warming. At the same time, we should have a short-term strategy, kind of a climate-ready plans, such as temporary closures during extreme hot years. In this case, we should, as I believe, is how the study, the evidence that the study gives us, that we should prioritize warm edge populations during marine heat waves. And finally, I'd like to finish by saying that I believe that those results, those patterns are also leading us to transboundary conservation, which is an imperative action against the impacts of global warming, because there is no one country that covers the entire distribution of a species usually. This is very rare. So if we only conserve those warm edge populations in one country, we can actually lose if other countries are exploiting the cold edges massively. So for the entire species range, it could be very bad news. And this is why we need this cross-boundary cooperation. So thank you very much for listening. If you have any questions, please contact me. And that's all.